Okay, so again, in sections 5 through, so far in chapter 5, you learn different integration techniques. And they've helped you to to explicitly find derivatives for a variety of problems, which is good. But in fact, there are situations where you have an integral and you cannot find the antiderivative. Okay, in other words, it's like impossible to find the antiderivative. In that kind of situation, if we have a definite integral and we can't find the antiderivative, definite integral has limits on the top and the bottom. We're finding the area underneath the curve. If we can't find the antiderivative, then, what are we going to do? Well, then we have to use approximation techniques. And that's what section 5.9 is about. It's called approximate integration. So, like, for instance, here are a couple of very famous integrals those integrals are impossible to integrate. Okay, 400 years has gone by and nobody has gotten the antiderivative for those integrals. You would be like a very famous mathematician if you could find an antiderivative. And I actually had a student, this was a long time ago, he thought he could get the antiderivative of that integral from 0 to 1 of e to the x squared dx. He thought he could get the antiderivative, and he says, I think I can do it. And he spent like 6 hours, but he couldn't do it, So don't spend time on that, okay? It says here that, of course, you have, well, let me make this a little bit. You have two situations where an antiderivative wouldn't work. One is if you can't get the antiderivative. That's what they mention here. They give an example of those two integrals. And the second situation, okay, is if you have a situation where the function's determined from an experiment through instrument readings or collected data. In other words, there's no actual formula for the function. That's the second situation. So we're gonna look at these two situations and see how numerical integration can help. So, okay. First of all, remember when you first learned about integrals, you recognize the definite integral as a Riemann sum. Well, it's a sum of rectangles underneath the curve. The heights of the rectangles are given by the function values, and the width of the rectangle is given by delta x. Okay, so that seems to be a good approach to approximate the definite integral, because we can always find the areas of rectangles and add up those areas. All right. So the question is, well, how are we going to add up the rectangles? How can we do it? Well, we have different rules. Okay. We have, like, for instance, and a picture is going to be helpful here, but we have like L sub n. L sub n. That stands for a left endpoint approximation. Okay, and then we have below it, we have R sub n. Okay, R sub n stands for a right endpoint approximation. Now, what does that mean? What does that mean? Well, let's go ahead and take a look at a few pictures. Okay, so figure 1 here, figure 1, all right, in the book, you have here a function, the function's in blue, in figure 1a, and you have left endpoint approximation. Okay, so this is section 5.9, figure 1. So you see there what they're doing. They have that blue function, and look at the rectangles and look at the heights. There are 4 rectangles, and how are the heights of the rectangles being determined? Well, if you look at every little interval. So you have 4 intervals, x sub 0 to x sub 1, x sub 1 to x sub 2, x sub 2 to x sub 3, and so forth. For each of these little subintervals, which endpoint determines the height? The endpoint on the left or the endpoint on the right in figure 1a?
Left.
Wait, say it one more time.
Which endpoint determines the height of the rectangle, the left endpoint or the right endpoint in figure 1? Yeah, the left endpoints, I mean, if maybe what I can do here, let me just go to the whiteboard here, and one moment. Okay, let me just, hold on, I want black. Okay, and that was right, Maria, your response, and the other student here. So, you know, you have an X and you have a Y axis. Okay. And you have this function here. Okay, this function. This is your function f of x. Okay, and let's see here. So on the x-axis, you have x sub 0, x sub 1. Okay, and we can draw, I guess, hold on, let me try to get the line here. Okay, so there's a rectangle, and hold on, it's kind of picky with this. This value here, right, is f of x sub 0. This value here is f of x sub 1, right? And maybe what I can do is draw another rectangle, but my picture, I'm going to have to alter the function a little bit here, kind of make it like this, okay? There we go. Okay, here's f of x sub 2, say. Here's x sub 2 right here. Okay, so you have, like the first rectangle here, what endpoint, the function takes on values at endpoints. Which endpoint here, x sub 0 or x sub 1, does the first rectangle, what determines the height of the first rectangle? Is it the left endpoint or the right endpoint?
The left.
The left endpoint. That's right. That's right, Renata. And what about the second rectangle? What determines the height? Is it the left endpoint x1 or the right endpoint x2?
The left again.
the left again. So you see the way I'm drawing these rectangles, we're using the left endpoints to determine the heights of those rectangles. And so if I add the rectangles up, I'm using what's called the left endpoint rule. The left endpoint rule. And if I go back to the book now, okay, so this is in the recording. Let me go back to the book. Okay, hold on here. You see there, the left endpoint rule or left endpoint approximation is in A. And then in B, they're using what's called the right endpoint approximation. There, the right endpoints determine the heights of the rectangles. You see that? Are there any questions on that? Okay, okay. Well, now we can also determine, we can also choose rectangles by looking at midpoints of the rectangles, and that's called a midpoint approximation. And you see, they're approximating the area under the curve with 4 rectangles in A, B, and C of this figure 1, and each approximation is going to give us a different answer, a different approximation. So the question is, of course, which approximation is best? Well, using rectangles is at times can be somewhat crude, but which do you think might give the best approximation of the 3?
C.
Yeah, I agree with Maria. I think C would probably overall give the best approximation to the area under the curve. Now, that doesn't mean the midpoint's always going to be the best, but the thing is, scientists, when they're approximating areas under curves, they want to try to be as accurate as possible. So, mathematicians came up with other ways to approximate areas under the curves. Okay, there's one way is, why not use trapezoids? See there how instead of rectangles, 4 rectangles, you create 4 trapezoids over the intervals. And you can find the area of a trapezoid, okay? The area of a trapezoid is, well, how many has it been a while since they've needed to find the area of a trapezoid? I mean, if we're going to add these, okay, it's been a while for Michelle and Tal, but do you remember the area of a trapezoid? I mean, you could look it up, but does anybody remember offhand?
1/2 times base 1 plus base 2 times height.
That's correct. That's right. Good, Maria. 1/2 times the sum of base 1 and base 2. Hold on. Well, times the height. And in this case, right, 1/2 times the sum of base 1 and base 2 times the height. So in this case, the height would be the delta x, and the bases are the f of x sub 0 and f of x sub 1, for instance, in that first subinterval. Okay, so given this, we come up with some formulas, right? Like for the trapezoidal rule, this is the formula, okay, for the trapezoidal rule. So based on n subintervals, the integral can be approximated by the trapezoidal rule. And that's going to equal delta x over 2 times what you see in the brackets there. F of x naught plus 2 times f of x1 plus 2 times f of x2, and so forth. Okay, so, and it turns out that the trapezoidal rule is actually an average of the approximations of the left endpoint and right endpoint approximations. Okay, so like for instance, let's I think the left endpoint rule, right endpoint rule, midpoint rule, that's easy enough. But let's go ahead and look at an example here. So this example, actually, we don't really need for the integral from 1 to 2 of 1 over x dx. We don't need to use a numerical approximation because we know the antiderivative of 1 over x. But the book wanted to start you off with something simple. So okay, well, all right. Let's apply this trapezoidal rule. So first of all, if n equals 5, that means you have 5 subintervals. So delta x is going to be the difference between the I want to say it the right way. Delta x, let's see if I can highlight that maybe. Delta x is equal to the n limit 2 minus the beginning limit 1 divided by n, which is 5, so 0.2. And that makes sense. If your curve goes from x equals 1 to x equals 2, and you divide 1 to 2 into 5 subintervals, each of those subintervals is going to have a distance of 0.2. Okay, so all right, so we have then 0.2 over 2 in the trapezoidal rule, and we have to evaluate the function at all of these values. So you start off at f of 1, and then 1 plus 0.2 is 1.2. So 2 times f of 1.2, and then 1.2 plus 0.2 is 1.4. Okay, and you get and then 1.4 plus 0.2 is 1.6, and so forth, and then finally you end up with 2. And so you see how they approximate this integral. You see how they do that? I mean, this is just an approximation to the integral, and it's probably not a great one because you're only using 5 subintervals. But that's the trapezoidal rule. That's the approximation t sub 5, which is 0.695635. All right, so really, this is just applying formulas at this stage. Are there any questions? All right, well then let's look at the midpoint rule. So the midpoint rule, for that, let's see here. Now the midpoint rule, they're letting, I mean, well, they have a picture below. Let me show you the picture. And I like to this because it'll be in the recording. Here's the function 1 over x, okay, and from 1 to 2, and there are your 5 subintervals. And the midpoints of the 5 subintervals are 1.1, 1.3, 1.5, 1.7, and 1.9. Okay, try to highlight it there. And so the midpoint rule says, okay, just evaluate the heights of your rectangles are f of 1.1, f of 1.3, f of 1.5, f of 1.7, and f of 1.9. Add them up and then multiply by delta x, which is a fifth. And that's how you get your answer. Okay, that's how you apply the midpoint rule. Are there any questions so far on this idea? All right. Well, of course, we would like to know how good our approximations are. to the true value of the integral. And in this case, we can actually find those errors exactly because we can compute the integral exactly and get an exact answer. But other times you can't find the exact error because you can't compute the integral. And in that case, we need to compute what are called error bounds. Now, error bounds, we'll get into those. We'll talk about those on Thursday's class. But I would like to move to example 5 because that deals with this problem where you have data. So let me go there. One moment. Let me find example 5. I'll just kind of piece through things here. I have to go to the next level. Oh, by the way, there's something called Simpson's rule. I should mention that. This is yet another way to approximate an integral. Simpson's rule, instead of using, like you don't use rectangles, you don't use trapezoids, you use parabolas. So you see there, they have, in figure 7, they have a curve, and they have 3 subintervals. And to approximate the function, they don't use horizontal lines or line segments. They use parabolas. And parabolas, you can see, because parabolas are curved in nature, they can approximate a function better that is curved in nature. So Simpson's rule is another rule that can be used. And they show how to, they derive it in the textbook. But I'm going to let you look at the derivation. You can, it'll take you a while to feel comfortable with it. I want to get right to the formula. So the formula for Simpson's rule is here. Okay, that's the formula for the Simpson's rule based on n subintervals. And n actually has to be even, by the way, for Simpson's rule. You have to have an even number of subintervals. I want to be careful about that. Yes, that's right. Wait, hold on. Hold the phone on that. N has to be even. N has to be even. So in that case, one moment. One moment on this. Hold on. Yeah, n has to be even, so that means you should have, I'm just looking here. Yeah, it'll be an odd number of subintervals. Right. So, so at any rate, there's the formula. And again, what they're going to do in example 4 here is they're going to use Simpson's rule to approximate this integral. Now, they're going to use n equals 10. So in example 4, it takes a little more effort. So the key is, like, you can, so like, how would you show your work on this? You would show your work just like you see here. You would write out the formula, write out the values of the function like that. But then you could use like a calculator or Desmos to get your final answer. And usually WebAssign is going to want 6 decimal places of accuracy on the answer. Just so you know, just so you're aware. All right, and that's the Simpson's rule. That's the Simpson's rule. So those are the approximation rules that you'll see in section 5.9, and we'll talk about error bounds in the next class. But I want to get to example 5 now. By the way, here's a note on Thomas Simpson. He was a weaver who taught himself math and went on to become one of the best English mathematicians of the 18th century. That's the 1700s. And that's the Simpson's rule. He popularized it in his book, set from 1743. So we're talking almost 300 years ago. You know, they didn't even have, you know, bathrooms back then, you know, with running water. Well, you know, hey, I'm not an expert on this, but, you know, at least in the movies, I don't see bathrooms with running water, you know, in the 1700s. So, but it's amazing, you know, back then, you know, they didn't have community colleges, so people had to educate themselves, right? Using books and things like that. Now, but you're educating yourselves. You have a community college to help you, and that's great. You know, so life's about progress. But back then, you know, if you weren't wealthy, you weren't going to a university back then, right? All right. So thank goodness we're here in 21st century. Now, let's go on here. Okay, estimating the amount of transmitted data, example 5. Okay, so let's take a look at this here. Figure 9 shows data traffic on the link from the United States to Swiss Academic and Research Network. Okay, the data throughput measured in megabits is measured in megabits per second. Okay, so it's data traffic on a link. Okay, and it's measured in megabits per second. So the D is megabits per second. So what happens at 9 a.m.? The t-axis goes from 0 to 24. That's 24 hours. And at 6 a.m., the data D, the value D of t, the function is small. But then suddenly there's a jump at t equals 9. What happened there? What account? And then from t equals 9 to t equals 21, data's pretty high. What happened at t equals 9 there? Why is there a big jump in the data? What's going on there? It spikes up to almost 8 megabits per second.
It's when the day starts.
When the work starts.
Good. That's right. That's when the workday starts, 9 a.m. And let's see. Now, basically at t equals around 21, maybe a little before. Okay, so you have people working into the evening, but then the data goes down. Okay, so, all right. What we want to do is we want to use Simpson's rule to estimate the total amount of data transmitted on the link from midnight to noon that day. Now, the function d of t, okay, maybe I can highlight it here. It's measured in megabits per second. Megabits per second, right? So megabits per second is a rate, right? Megabits per second is a rate. Now, if we want to use Simpson's rule, okay, if we want to use Simpson's rule to, hold on. If we want to use Simpson's rule to estimate the total amount of data transmitted on the link from midnight to noon on that day, what do we have to find? Being that the function d of t that's drawn here represents rate of megabits per second. To go from a rate of megabits per second to get to megabits, what do we have to do to the function d? What do we have to do?
Find the integral.
Good. That's right, Nathan. We have to find the integral. So now this becomes an integration problem. But in this problem, we don't have a function to work with. We just have a picture of the function, but we don't have a formula. But still, based on the function itself, we can collect data and try to estimate the integral. And we're going to do it in this case using Simpson's rule. So what we do then, let's go down a little bit here. What we want is in our solution, and I'll highlight all this good stuff here. We want units to be consistent, and d of t is measured in megabits per second. Megabits per second. Okay? So that means that in terms of our time, if we want to estimate the amount of data transmitted on the link from midnight to noon, that's 12 hours. That's 12 hours, but 12 hours is 12, 12 hours is 12 times 60 minutes. But in terms of seconds, 12 hours is 12 times 60 minutes. 12 hours is 12 hours times 60 minutes times 60 seconds. And so that's how you get then the final time is 43,200 seconds. So the integral, the area that we want to find is the integral of the dt, sorry, the d function with respect to t, where t goes from 0 to 43,200 seconds. Is that okay so far? I want to make sure that you're comfortable with everything so far. Are there any questions at all? Okay. All right. Well, then let's see. Now we have to go to the table, and we are going to be using. Let's see. I'm just looking here. They don't tell us how many subintervals, but it would make sense if we're going from midnight to noon. It might make sense. I'm sorry. If we're going from midnight to noon, it might make sense to, that's t equals 0 to t equals 0 seconds to t equals 43,200 seconds. It might make sense to use 12 intervals because they're 12 hours from midnight to noon. So let's look at the table here. Okay, so this is nice. They break the table up in terms of hours. Okay, and for each hour, they give the number of seconds. Well, so the 1 hour is 3,600 seconds. 2 hours is 7,200 seconds. And then they give the value of our data function at each for every hour. So we have this data, and we now can apply the Simpson's rule to the data. Okay, and that's what they do below. So let me see, maybe I can make this a little smaller. Hold on, everybody. I'd like to try to have everything show here. Yeah, that works. So take a look at Simpson's formula below. And are you, well, hold on. I don't have the whole formula shown there. Let me go up a little bit. There we go. Maybe, there we go. It's all there. Everything you need. Okay, so on, let me just see here if I can highlight that. I've highlighted the formula, and remember, you can use your Zoom link on the right of your screen to make that a little bigger if you need to. Are there any take a look. Are there any questions with, how they're plugging numbers into the formula? So of course the formula is given in the textbook. It's given in the textbook, but like in the formula, like 3,600 divided by 3. The delta x is 3,600, or delta t, I should say, because 1 hour is 3,600 seconds. The d sub 0, you start off with 3.2 megabytes per second at midnight. And then after 1 hour at 3,600 seconds, you have, hold on here. Yeah, you have 2.7 megabytes per second. After 3 hours, you have 1.7 megabytes per second. And do you see how they're just plugging things in from the table, how they're using the table, and then you just plug the values in? I mean, are there any questions on that? Who's feeling good so far? Maybe give me a thumbs up if you're okay. Nicole's comfortable. Leping, wonderful. Audra, and Sophie, and Sean. Okay, very good. And Baraka. All right, so very good. So, then you just evaluate this. You just evaluate this. Okay. And, naturally, you can use your TI calculator. You can use Desmos. That'll be fine. Turns out you're going to have, that's all going to equal 143,880. That's value. And so the total amount of data, total amount of data, let me blow that up a little bit now. Total amount of data transmitted from midnight to noon is about 144,000 megabits or 144 gigabits. So see, this is a problem where you have to find the answer to this question, you have to use numerical approximation. Okay, you have to, because you don't have a formula for your data function. How many think this is like absolutely cool? I mean, okay, Jacob likes it. I mean, you're engineers, you're training to be engineers and scientists and computer scientists and all your fields. This is great stuff. Are there any questions? Any questions? Okay, I'll stop the recording.